construction stuff because I really don't like it. I really just like to do service now, but ductwork sizing is very important. And I know that there's some easy ways to get start getting a handle on it. It's going to get much more complicated as you get deeper and deeper into it. But for the simple stuff like residential and even light commercial, there's not a whole lot that goes into it. Now, what we can do, we've all heard about friction rate charts, possibly. If you haven't, I mean, if you just know nothing about ductwork design, it's okay. This is gonna work for you guys too. We're gonna start in a very simple way. Typically, to do a proper duct design, you're gonna have to know what blower you have. You're gonna have to know the capacity that's required, meaning you're going to do that load calculation first. And let's say you have a 3-ton machine that load calculation calls for. So a house needs a 3-ton machine. It's going to push, let's say it's going to push 1200 CFM. Typically, when we're talking about tons of AC, you're working with a nominal 400 CFM. Now, a lot of times ACs will use around 350, but between 350 and 400 is a pretty good number to use. So we use a nice round 400 a lot of times. So if we're talking about 3 tons, we'll go with 1200. So 1200 CFM has to be distributed all across the house. You're going to divide it up and distribute it into each area as needed. So the ductwork's going to have to be properly sized. So that's where the question comes into, what blower do we choose? Now, it's really easy because a lot of times people have like, well, we have this, like a Goodman has an ARUF 36 or 37 now probably. Delivers 3 tons worth of air, and you'll see the blower chart and you'll say, okay, I need 1200 CFM, and it'll give you what CFM you get on what speed under what static pressure. And let's talk about that. Blower motors, there's a lot of different kinds. There's the PSC motor, which is a permanent split capacitor. It uses a capacitor. Typically they have 2, 3, 4 speeds, and you'll have to choose one of those speeds and go by the install manual to set up the airflow. Especially if you're measuring with static pressure, because you're going to need some sort of baseline. If you throw some other aftermarket motor in, then it's anyone's guess what the airflow is. You're going to have to use a different method to get the airflow. You're not going to be able to sit there and put that motor in and say, well, it's the exact same standards as the previous motor, because it's not going to be. It's going to be a best fit sort of situation. So you have your air handler, you have your furnace, and it's going to have a blower chart. And it's going to tell you what CFMs you're going to get at what speed. And then at the top of the chart, you're going to see static pressure. So what's that mean? Static pressure is basically the pressure that's created from the air pushing on the duct. The more pressure, the smaller the space, as you could guess. If you have 1200 CFM going into a 14-inch duct, it's going to create more pressure than if you had 1200 CFM going into an 18-inch duct. Because an 18-inch duct is larger, that air is allowed to spread out and can dissipate into the branches faster. You're not going to have that build up of pressure that you would in 14-inch duct. Now 14 inch is too small for that. But you're going to have to design that system based on how much static is available on that blower. And here's what I mean. And this is the complicated part. We're going to kind of touch on this, then we'll get onto some rules of thumb that'll help you in the field while you're learning the other stuff. So you have a blower that, say, this pushes 1200 CFM on 0.5 external static pressure. Now, if you're using an air handler, that coil is included. But if you're using a furnace, the coil is not included because that's a separate unit. You're going to have to add in for pressure drop. So you're going to start with 0.5 static pressure. And there's going to be some things right off the bat that take away some of your static pressure that's available for the blower. And what that means is the remaining static pressure is what you have left to size ductwork with. You start with 0.5 because that's what you picked out. And you have to take off filters. They're going to have a certain pressure drop. And let's say your filter, and I'll write it down here with me. Your filter is going to have a pressure drop. I'll get my pad out. We start out with 0.5. And your filter is going to have a pressure drop, let's say, of 0.05. So you got 0.05. And your dampers and supply grills and return grills are going to have an overall pressure drop of 0.10 or 0.1. So you have all those. Let's add those up just to see what we got. You take those away. See, we start with our 0.5. We have to take away the 0.05 and 0.1. So we're basically down to 0.35 available static pressure. Now the 0.5 is external static pressure for the blower chart, but this 0.35 is our available pressure. After we factor in those devices, that's what we have left to find out what our friction rate has to be in the ductwork. So we have 0.35. So we'll go down and find our friction rate, and then we can use our ductilator to size up each individual run. But we're not going to do that on this video. This is just kind of laying the framework for later. We'll do more videos on duct design, but I know everybody has to start somewhere. They have to learn the basics, because when you go to work tomorrow, you're not going to have time to wait for me to do the rest of the duct design series. You're going to want to know something about how to size ductwork. So there's some rules of thumb. But that's basically, when you're designing stuff, especially on a higher level, when I do the commercial load calculations, like I've done a few duct design and load calculations for Great House, and I had to employ some of this stuff because I'll get a design external static pressure for a blower, and I'll have to work back through it. And some of the stuff, you're not going to know exactly what the pressure drop is. You're going to have to use sort of your best guess to what the pressure drop. You'll look up something similar. You'll look up what you think they're going to use, and you have to design for it. That's why some of the jobs are always kind of, you never know what's going to happen, because they'll come in and say, well, we're going to have to downsize your duct because it won't fit, or we're going to need you to use a high static blower, which some systems have a high static blower, so they can deal with 1 inch of static or 2 inches of static. But that's not today, gentlemen. That's not today. Let's look at some easy to understand residential stuff. Residential duct sizing. We're talking about what should the duct size be per ton. So we're saying that we have a 2-ton machine. What should we be putting in? Now a lot of guys know that 210, hey, I usually run 14 if you're doing round, or you can run 20 by 8 if you're doing rectangular duct. There's all sorts of variations. You can run, 15 by 10, 20 by 8. You just have to have a certain amount of square inches. And that's where this rule of thumb comes into play. 6 inches per 1,000 BTUs in air conditioning. 6 inches per 1,000 BTUs. So we have 2 tons. We have 24,000 BTUs. 24,000 BTUs, or 24 times 6, equals 144. That's how many square inches our duct has to be. And looking at a chart on different ductwork sizes, we can see that I have a little chart I built right up here. And our 14 inch is 154 square inches. So we have 10 inches to spare. But if we step back to, let's say we went back to 10, we only have 79 square inches. So it's much too small. So 14 is the proper size duct. Keeping in mind that when we look at ductwork on the supply, we're talking about clean, slick metal. We're not talking about flex. If you use flex, the friction rate on flex is 2 or 3 times what it is for metal duct. So you might come through and say, well, the blower might be able to handle running the flex the same size on high speed. You might have to step it all the way up to be able to compensate. But the best thing is, that's why people say oversize the returns. You have a 2-ton system, run a 16-inch return or an 18-inch flex return if you're running flex. It'll make it quieter to run flex. You won't have that transmission down the ductwork because a lot of your supplies will already be flex, so you won't have that problem on that end either. Step it up a size or 2 on the return. You don't have to go 20-inch on 2 tons, but you can step it up to 16 or 18-inch flex. Or if you're branching into 2, maybe you run, 2 12s or 2 14s or something like that. Just to keep that friction rate in mind, because there's a lot of friction on the inside of flex. Just imagine that all that helix wrapped in and in and in and in like that is going to, push back on that airflow and cause a lot of issues. So especially when you undersize flex, it really shows up real bad. Not as bad as with metal duct, because metal duct is so smooth. Let's look at 3 tons. So if we have 3 tons, we have 36,000 BTUs, which is 36 times 6, which is 216 square inches. And I hope all this math is right, because I wrote it down here, and I've been known to miscalculate, because I do it by hand, because I'm such a damn stickler for that crap. 216 square inches. Now if we look up on the round duct chart I have up here, if we go up to 16 inch, it used to be 16 inch was the rule for 3 tons here, so you can use 16 inch round. When we look at it, it's only 200.96 inches, or 201 square inches. So we're about 16 inches short, which isn't a huge deal. And if you used an oversized return, I bet you wouldn't have any problem with it. But because a lot of people don't, they just kind of throw in the worst possible duct system they can for some reason. I don't know why, it just seems that way. Having the proper size will make even more difference. So, you use an 18-inch duct on a supply and maybe a 20-inch or 2 16s on the return. Because keep in mind, even though your round sizes step up little by little, the amount of space inside those ducts goes up quite a bit because you're expanding on 2 sides. For example, 10-inch is 79 square inches area. 16 is 200 square inches. You go up 6 inches, you've gained almost 120 or 120 inches in area. You go up to 20, it's 314 square inches, which brings us to 4 tons. You have a 4-ton AC. It's got to produce 48 times 6, because 48,000, 48 times the rule of 6 here, we have 288 square inches. So we're going to have to use a 20-inch duct. If we're using square duct or rectangular duct, we're going to have to use by 10, 30 by 10, unless we expand it beyond 30 inches, because 30 by 8 is only 240 square inches, and that's 48 inches too short. So if you're putting your supply into a 240-inch duct, it's going to have some issues. It might have some issues with turbulence. It might have some issues with velocity and noise. So a proper size duct would be 30 by 10. Or if you want to step it back to some by 12, like a 25 by 12 or something like that, you could do that as well, because that's 300 square inches. So as you can see, based on what you hear from me now, you go out in the world here and look at these duct systems, a lot of them are undersized. And a lot of the blowers, and this is my opinion, stuff I've seen personally, a lot of the blowers from back in the day are beefy. They're more powerful. You see, they draw more amps, they push more air, and then as time goes by, we want to make things more efficient, draw less electricity, we enlarge the ducts. We enlarge the ducts, we can step back the blower's capabilities. It can run at a lower amp draw and still push the same amount of air because we don't have all that static. The duct works larger. The problem comes in when guys take the old system components out, not the duct system, just the equipment itself, put the new stuff in. Because the new stuff is then in a lot of trouble trying to push air through those duct systems because it can't handle it. Because these blowers, especially some of these X13s, I look at the blower charts and you put a little bit of static on them and they just kind of fall apart. They don't do anything. It's just kind of sad. And for all the talk about X13 motors, I mean, taking the PSC motor out is not just, or putting a PSC motor in when they fail. A lot of guys have seen my videos. You see Israel just did a video on that. Replacing them is just not good because they're more reliable, the PSC motors anyway. It's because you can actually put in a motor that can push against some static. My favorite motor is a half horsepower 2.9 amp motor that I use that I purchased at Johnstone because it will allow me to push the proper amount of air. In fact, that's the one I carry so I can put it into downshot, single wide, and double wide furnaces because it can produce enough air against all that static pressure in the supply duct. If you go back with a normal blower, or let's say you take a blower out and it says 1/3 horsepower on it, but it says 2.8 amps. And you go to your truck and see your 1/3 horsepower, and we're talking 240 volt motors, 1/3 horsepower produces 2.1 amps or something like that. And you say, well, I'm using the same horsepower, whatever. I see it a lot. Hell, it's stupid. I used to do that myself back before I, wised up. That blower can't handle that. It's not powerful enough. You can tell when you put the 2.9 amp blower in, it's going to pull more electrical load. It's not as efficient as the previous blower if you're replacing an X13 anyway, but it's going to do the job and to me be more reliable. So it's not just a question of when you go out to do service, are you having the proper airflow? If you don't have the proper airflow, it's not always, hey man, you got to change out your duct system. You don't actually have to do that. I mean, you could change blowers, but then that's going to be on you to design the blower that's proper for that situation. If it doesn't work or it's too loud, of course they're going to be mad at you. And if the ductwork is too small and you're trying to compensate with a blower, it has the possibility of being too loud. But it may work better than it ever has before as well. So it's going to be a trade-off. It depends on where the system's located, where the blower is located. Is it sitting in a closet, or is it in a package unit outside, or is it so far away they won't hear it? But I find that a lot. I changed out a blower on a gas pack. It was half horsepower. It was a 3.5 ton machine, PSC blower. And the duct system was way too small. It was like a 16-inch flex duct running to it on 3.5 tons. So it was not getting the proper amount of air. So what I did was I wired it up and put in a 3/4 horsepower blower. Now this beefy guy was going to push some air. I mean, it wasn't quiet, but it was outside and it didn't bother anybody. And the guys inside were like, wow, we've never seen this much air before. So, yeah. And it's one of them things where it's bad on so many fronts because it's a duct system and they have headers running upstairs to bring heat and cooling to the upstairs 2 bedrooms, and there's no zoning. It just, no air gets up there. You can tell it doesn't work very well. There's a filter upstairs, a small filter grill upstairs, and 2 filter grills downstairs. The filter grills downstairs were covered in dirt. The filter upstairs looks like it's never been changed before because no air moves through the grill. Or in fact, no, I had put that filter in a year prior, and it looked like the day I put it in because no air is moving. And so, of course, I told those people that they had to make some adjustments because it's not anything that a blower can solve. It's more about the actual delivery of air through the duct system. It's just not getting to the right places. But we'll see. That's for a different day. But that's our first video on duct design. We'll talk about, velocity. We'll talk about friction rate. We'll talk about available static pressure some more, total external static pressure. If you start understanding the little bits of it at a time, just like me, you'll start putting the pieces together. And when I see all the stuff laid out for me, it's like, whoa. It's like, what is all this crap? But when you start seeing the little pieces and how they fit together, you can start saying, okay, I can understand that. I can see where it's going. Just basically think about it. A blower is sent to you and it's designed, say, this blower can push against this kind of ductwork and give you this amount of air, basically. And they're telling you through static pressure. I said, if you have this much static, this much pushback on your blower, it can still give you X amount of air. So if your ductwork's too small, you're not going to get that air. If your ductwork's larger than it says, or less static than it says, you're going to get more air. And you can change your reference point on the chart. But you'll
You're a bad man. You're a bad man. The bad man. You're a bad man. The bad man. You're a bad man. The bad man.
We got you. Oh, we got you. We got you. Oh, we got you. You're a bad man. man. Sup?
Oh, I like the sup. Sup, yo! This is my dog talking to you live from the signal. Oh.
Guys, we are looking at the Southwire 15-inch open-top tool bag. It's a really great tool bag. We're going to take a look at all the different compartments, the overall size of it, while we listen to my cat's meows in the background. It's the 15-inch bag. It measures about 14.5 inches long. If we look at the side, we can see that that measures right around 9 inches or so. And from top of the tool bag opening here to the table, we have just under 11 inches. So measuring the top then, it's around 8. Looks like 8 by about 14 or so, 8 by 14. We look at the front of it, we have the little strap to put electrical tape on it. I'll take my tapes, like I have my high voltage splice connection tape here. I'll put it on there and you'll hook it up like this. Keep your tapes in the right spot. There's a number of pockets on the outside. We have one small pocket here, a larger pocket on top. We have a large wide pocket. It measures about 8 to 9 inches long, going all the way across the middle section of the front. 2 larger pockets on top of it. We have another 2 pocket connection here. We have one in front of the other one, is slightly taller, just like on this side. So we have 1, 2, 3, 4, 5, 6, 7 total pockets on this side, along with our strap for the tapes. Let's go around to the end. On the end we have 2 pockets, 1, 2 equal size. They're about 3.5 by 5 inches tall. Plenty of room right there. In fact, I have something in this one. Let's see. I think it feels like I have some nylog in here, but I can't get it out. There we are. Yep, some nylog. So that's a pocket. That's a pocket can fit nylog. You got proof right there. You can see we have a strap that goes on this bag, connects on the end, has a nice clip on it. Clips onto the D-ring right here, so you can take it on and off if you don't need the strap. Spinning around to this side, we have one large pocket that goes the length of the bag. It's about 6 inches tall. Open it up, a lot of room in there. If you have something else you want to put in there, I think I used to put like you can fit like a meter like this in there. You can put different screwdrivers, maybe a meter, temperature meter, like the DTH35 here. I mean, you could put that in there. Things like that. You want to stay completely enclosed. You don't want them to get dirty. It's a good idea. We go around to the other end. We have the same situation we had on the first side. We do have our metal support if you want to hook a tape measure. You can put one right there. Same 2 pockets as the other side. A lot of room. So quite a bit of space here. You'll see the bottom. Got a rugged plastic design here. That'll keep everything dry. You won't have to worry about sitting your bag in the water, in the mud, or anything like that. This will keep it safe. So it's a really nice bottom here. Keep things protected. I had the bag in service for a while now. You can hardly tell it's been in service. I try to keep them fairly clean, but it's turned out to be a good bag. So we're going to take a look in the top of it here and see what kind of supports we have inside. All right, we're looking at the inside of the bag. There are 3 dividers that are inside the bag. Each one of those is Velcro to the side. I did not have an issue with the Velcro coming undone and moving. Now you can take it loose if you want to remove one of the dividers. You can take it out. The Velcro is on either side at a 90-degree angle against the wall of the bag. On the end of the bag, there are some little areas where you can tuck screwdrivers or pliers. Here's an example of a nut driver. Fitting a nut driver down into the bag like this. There are some little areas where you can sit things like that. Each divider has pockets on it. 2 large pockets. 1, 2, 3, 4, 5, 6. So with the 3 dividers, you have a total of 6 pockets. Each side has little hanging areas for nut drivers and screwdrivers. Inside of each divider, you have the same thing. Let's take one out and take a look. But you can see there's 4 different compartments in for whatever way you want to arrange your tools. This is an example of one of the dividers. You have two large tool pouches here. You can put your wrenches and tools into, however you want to do it. Of course, there's two more like I just said, and they are removable. On the other side, you have these little connectors here that you can fit tools and pinch them in between, like screwdrivers, pliers, however you want to work it. But you'll have 1, 2, 3, 4, so a total of 12 on the dividers, and 1, 2, 3, 4, 1, 2, 3, so 7 more on the end, 3 more on the bottom there. So you could actually stuff tools in and go ahead and stick them through the bottom connectors as well, however you want to work it. But the bag has been tough so far. I've had no issues with durability, no issues with the Velcro coming undone. In fact, it's a chore to get it out because it's so well positioned inside the bag. We have the field piece SRS2 out. We're going to measure the weight of the bag. Have it sitting right out front here. The total weight of this bag is 5 pounds, 14.75 ounces, so real close to 6 pounds. As a comparison, as a smaller bag with just a couple items in it here, a little small thing, my little electrician's tote is about half of that, a little bit less, at 2 pounds, 1 ounce. And another comparison, here's my Husky bag with the tools in it. Now this isn't comparison apples to apples because I have stuff in it, but just here's an example of what a full tool bag will weigh. This one is almost 20 pounds, 19 pounds, 15 ounces. So it is a hoss because it has all my tools in it and probably some stuff that I don't need. I'll probably carry a smaller bag inside. I've used all of these bags. I tend to acquire tool bags. As you can see, guys, I'll pan over if you can see it. Over there you can see another AWP bag. I just keep on using tool bags. I cannot stop. So, that's about it for this. Here's the Husky bag. Got my stuff in it. I haven't used it in a while. I just loaded some stuff into it to try it again. But the Southwire gets the thumbs up of approval. A good bag, nice bottom, protected from the elements. Plenty of compartments for what I'm doing, which is service work. And you could probably actually use it for install and get a smaller one for service as well. Alright guys, thank you for watching and I'll see you on the next one.